Okay, welcome. We are going to go over the homework on volume by shells. This should be the last video of the year. This is the last video that I'm going to make for school year 2019-2020. I'm very excited to be done. Let's begin. Number 9 says, I got a curve. Y equals 4x minus x squared. X equals 0. I think a region is being described. Y equals 4. Directions. Use the shell method to set up and evaluate the integral that gives the volume of the solid generated by revolving the plane region about the y-axis. Okay, let's go. So, alright, so this curve 4x minus x squared, this really looks like negative x minus 4. So I think I already know this curve pretty well. There is a root at 0 and a root at 4. And yeah, over here at 2, it's going to be up here at 4, but okay, never mind that. So we have this. It's just an upside down parabola with, wait a second, number 9. For y equals x equals 0, y equals, oh, this is actually not kind of what I was thinking it would be. X equals 0, y equals 4. Okay, so this picture is going to be a little bit small. X equals 0 is the y-axis. Y equals 4 is this line. And so there's this point 4 comma 2. And therefore, I had to read this a couple times, but it seems now that the region under discussion is this one. Okay, and so, good. So I have this parabola. This parabola is y equals 4x minus x squared. And now I want to, what am I doing again? I'm finding the volume of the solid formed by rotating this region about the y-axis. Okay, so if we rotate this thing about the y-axis, first of all, what shape is formed? I guess it's going to be some kind of one of these sorry pieces again, or whatever. Or horns or something, and we want to find the volume of this solid. Now, we could, so we have the formula expressed as y equals 4x minus x squared. In other words, it came to us in the kind of normal way that a parabola comes. You give me an x value, this formula will output the y value. I could, I suppose, solve for x as a function of y, and then I could partition this region up into horizontal rectangles, and I could do this with disks. But that would be kind of annoying, because to solve for x, I would have to like complete the square here, and I would get all kinds of radicals and stuff. It's not too bad, but I don't want to do it. Instead, I will use the method of shells. And the method of shells just says, okay, partition your region up into rectangles, and let that be the representative rectangle drawn at point x between 0 and 2. And since this entire shape is being rotated about the y-axis, then I can find the volume of this shape by splitting it up into an infinite number of infinitely thin shells. And a shell is just what you get when you rotate to this representative rectangle around the y-axis. So you know you're getting a shell when your representative rectangle is parallel to the axis of rotation. And here we drew our representative rectangle vertical just because this is the form that the function came in, so it seemed like a good thing to do. Plus they just told us to. Okay, so what happens is we get this shell. And, okay, that doesn't look so good, there we go. We get this shell. And what is the volume of a shell? Well, okay, we did this whole thing in the video that if you give me, but maybe worth doing again or something, if you give me a shell, which is after all just, I don't think I've ever drawn this particular picture before. Okay, so what is a shell? It's just a tiny thin cylinder minus another cylinder. And if this shell has a certain radius and a certain height, then and a certain thickness, then what's the volume of that shell? Well, the simplest way to kind of remember it is to just think of that shell as being sliced and then just sort of opened up. And if you slice and open it up, then what you get and unfold it, then, okay, I don't know how accurate that was for the particular one. Okay, whatever. Then what you get is a like sort of piece of paper, so to speak. You unfold that toilet paper roll into like a long, thin strip, and you spread it out. Well, this is just h, the height of your shell, and the thickness of this is just delta r, and then the length is just the circumference of the circle which was unrolled. Okay, so you don't even really need to memorize this. You should sort of think about it for a second. Oh yeah, what is a shell? You sort of unroll it, and then of course the volume of this is just 2 pi r times h times delta r. Okay, so in this case, I need, maybe it's best not to write that exactly there, because I need I need a couple things. I need to know the radius of this shell, and I need to know the height of the shell, and then that's pretty much it. So what is the radius? I can do that first. What's the radius of the shell? Well, the radius of the shell is just the distance that the representative rectangle is from the axis of rotation, so that's just x. And the height of the shell is just the length of that representative rectangle. And, well, what is the length of that representative rectangle? It's the difference in the y-coordinates between the line y equals 4 and the parabola. So it's actually like 4 minus 4x minus x squared. That's the height of the representative rectangle, thus that's the height of the shell. And so, when I go to calculate the volume of this thing, I guess I'm just going to do this right here, it's going to be 2 pi, the radius is x, and the height is 4 minus 4x plus x squared. And the thickness of the shell is just the width of the subinterval, which is dx. This is, think of this as the circumference of the shell when it's unrolled, the height of the shell, the thickness of the shell. All together, when you multiply those together, you get the volume of the shell. And if that's the volume of just one shell, then I'm going to integrate along the x-axis from 0 to 2. And that should give me the sums of the volumes of all those shells, and thus that'll give me the volume of my shape. Okay, there's actually some work to do here. So this is 2 pi, integral from 0 to 2. Let me multiply this through. I get x cubed minus 4x squared plus 4x. Okay, and now I just do this integral. So that's x to the 4th over 4. Minus 4x cubed over 3 plus 2x squared. And then that whole thing is being multiplied by 2 pi, but is also being evaluated at 0 and 2. Okay, let's just do this. What do we get? When we plug in 2, 16 over 4 is 4, minus, here you get 32 thirds. And here you're going to get 8. So, whatever that is, man, it's 12, which is 36 thirds, minus 32 thirds. So I think that's 4 thirds in there. And I guess that the answer is 8 pi over 3, which seems kind of reasonable. Let's see what the answer key is. Yeah, good. Whew. Okay, one down, bunch to go. That was a nice recap of the whole thing. Okay, so more or less all the problems on this homework involve shells, but there's some, the more methods you learn, the more you have to sort of think about which is the best method to use in any given situation. I don't know. Alright, let's just keep going. 11. I think this problem is a little dumb. It says, it gives you this curve, y equals 1 over root 2 pi. So you might be thinking, come on, e to the negative x squared over 2. And then it also gives you y equals 0. x equals 0, x equals 1, x equals 0, x equals 1. Okay, I think this is a famous function. I keep remembering to look this up. I think this is like some kind of, I think this is the formula for like the normal curve. I should probably know this sort of very, very basic stuff, but I don't. But it's something involving, this is a famous function that comes up in probability and statistics. What does it look like? Well, okay, it's even. The bigger x gets, the smaller this function gets. End behavior is 0 in both directions. Blah, 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 blah. What are we supposed to be doing again? Find the volume. Volume of what? The volume as this curve. Okay, if I plug in 0 into here, I get e to the 0, which is 1. So we get 1 over 2 pi. So 1, so not too big. And I think it's going to be smaller just everywhere else. So x equals 0, x equals 1. When I plug in 1, I get, okay, this is just not, it's not worth it coming up with this. I'm going to get some kind of thing like that. I think that's even the correct curvature, just from memory. Okay, what's happened so far? Not much. We just have this region. It's the region bounded by x equals 0, x equals 1, y equals 0, and the curve. Okay, and what am I doing with this region? I'm rotating it about the y-axis. Here, it would be extremely difficult to do this problem with, well, maybe that's a little bit of an exaggeration. It would be difficult to do this problem with disks. For starters, you'd have to split up into two integrals because there's sort of different representative rectangles sideways in both directions. Anyway, in this case, because I have the function right here, it's just extremely beneficial to be able to just draw my representative rectangle like this. And now, since my representative rectangle is going to be parallel to the axis of rotation, that means I'm using the shell method. What does this shape look like that we're finding the volume of? Well, it's just going to be some kind of thing. Let's just, I don't know how to describe it. I won't try. But when that representative rectangle, which is at point x, we draw that representative rectangle. When it gets rotated around, it forms a shell. And as we just discussed, to find the volume of this solid, we'll find the volume of the shells and add them all up. To find the volume of a shell, we need to know two things. We need to know the radius of the shell. In this case, the radius is x. And we need to know the height of the shell, which in this case, the height is just that function. So actually, this problem is very easy to, I think, understand. This is an easier problem even than the previous one. But this integral is a little bit interesting, so let's do that. So what are we doing? We're doing 2 pi r, the radius, which is x, 2 pi r h. And h is just the height of the function. And the height of the function is 1 over root 2 pi e to the negative x squared over 2, and then dx, the thickness of the shell. So it's 2 pi r h dr, or something like that. Okay, and now that's the volume of one shell, so we integrate from 0 to 1 to add up the volumes of all those shells. Alright, so now I just need to kind of zone out and do this integral. If I pull the constant out, I get 2 pi over root 2 pi, which is just root 2 pi, integral from 0 to 1. And then I'm pretty much left with e to the negative x squared over 2 x dx. And the only reason why I left this problem in the homework is because it's kind of nice to keep flexible with your integration by substitution. And so I'm going to let u be negative x squared over 2. Du is therefore negative 2x dx. Yeah, whoa. No, just negative x dx is what I meant to say. Boom. Because when you differentiate 1/2 x squared, yeah. Okay. So there's already an x in there, so I just need to stick in a negative and undo the damage. And what I'm doing here is I'm solving this integral by substitution. So I get root 2 pi, and here I'm going to get now negative x dx is du, and this is just e to the u du. Okay, but I have to change my limits of integration. what is when x is 0, u is 0, but when x is 1, u is negative 1/2. And now these are sort of backwards, so I pull out a negative and flip them back again, so this becomes root 2 pi integral from negative 1/2 to 0 of e to the u du. Well, that's not too bad because the antiderivative of e to the u is just e to the u, so I get root 2 pi times e to the u evaluated at 0 and negative 1/2. And that is going to be root 2 pi times e to the 0, which is 1, minus e to the negative 1/2. So maybe if you want to be cool or something, you write this as root 2 pi times 1 minus 1 over root e. That should be our final answer. I bet that's just right. Yep, looking perfectly good. Okay, whew. Alright, then I hope they get sort of a little more interesting. 5 problems left to go. 23. No, this is not wildly interesting, this problem number 23. But nonetheless, we can do it now. Perhaps I should just erase, I might need both boards for this. Just erase everything. Yeah. This is a problem that I think is, well, I think it's kind of hard, potentially. If you don't understand shells very well, you could sort of misapply the theorem. So let's go. 23, same function. Y equals 4x minus x squared. Same curve, I guess I mean. And now 23. Y equals 0, okay, and y equals 0. So the directions are, use the shell method to find the volume of the solid generated by revolving the plane region about the given line. But in this case, the given line is x equals 5. So I'm rotating about x equals 5. Okay, so that's like a whole new thing. If I'm rotating about the line x equals 5, then if this is the parabola with roots at 0 and 4, it looks like that. But then x equals 5 is like over here. So this is the line x equals 5. And this is the line that I'm rotating about. So I have, I think I've followed these directions carefully. I have this parabola. Here it is. I have the y-axis. Those two things define a region. This is my region. What am I doing with this region? I'm rotating it about the line x equals 5. And okay, so what kind of shape am I going to get? Some sort of, let's see, that'll be like 6, and then that'll be like 10, or whatever. And what we're going to get is some kind of crazy thing like that. Some sort of kind of like a circular valley kind of thing. All right. Let's do it. How? With shells. So here's where we have to be sort of careful. I'm going to draw a representative rectangle, but notice that I have to sort of pick an arbitrary x value on the x-axis, and that's, I'll just call that x. So, well, when I draw that representative rectangle, what happens when it gets rotated around x equals 5? A shell is formed, and that shell looks like this. So shell, shell. Okay, but now when we go to analyze the shell and figure out its volume, we need to know its dimensions. And the dimensions of this shell are, well, we need to know the radius of the shell and the height of the shell. I think that the height of the shell is easy. The height of the shell is just going to be, for a given x, it's just going to be the parabola, 4x minus x squared. But the radius of the shell is not just x anymore. The radius of the shell is the distance that the distance from the axis of rotation. So it's the distance from the representative rectangle to the axis of rotation. So I have to look at that as my radius. And what is that? Well, if that's x, and that's 5, then this is 5 minus x. The representative rectangle For a given x value, the representative rectangle is 5 minus x away from x equals 5, and so that is the radius of the shell. So now, when I go to do the integral, I have to say, okay, it's going to be 2 pi, the radius, which is 5 minus x, times the height, which is 4x minus x squared, times the thickness of the shell, which is dx. And now I'm going to integrate from 0 to 4, because that's really what I've done is split up this interval up into 2 subintervals. And I just really don't want to do this integral, but I guess I'm just really going to now. So this is 2 pi. Okay, I find that distracting, so I'm going to pull a negative out of both of these, even though that feels like a wasted step. And now I guess I just crank it out, right? So that's x cubed minus 4x cubed minus 5x squared plus 20x. Okay, so I take it back. This is not that bad. Yeah, it just isn't. Just double checking everything. X cubed minus 4x squared minus 5x squared minus 4x cubed. Yeah. Oh, no, that should be squared. Oh man, hold on. X cubed minus 4x squared minus 5x squared plus 20x. Okay, that's right. So now what we have is 2 pi integral from 0 to 4 of x cubed minus 9x squared plus 20x dx. Okay, this is just, now we just do it. So we got x to the 4th over 4 minus, you go up to the power of 3 and divide by 3, so it's just going to be 3x squared plus up a power divide, so 10x, man, 3x cubed. Up to 3 jom jom, and then up to 2 da, yeah. So all this evaluated at 4 and 0, and it's a 2 pi here. Oh man, these numbers are so big. So 4 to the 4th divided by 4 is just 4 cubed, so that's just 64, minus, there might be other better ways to do this. Yeah, I mean, when you have really big numbers like this, and they just kind of suck, the smart thing to do is to like do something about that. So like maybe write this as x squared over 4 minus 3x plus 10. Is that better? I guess that's probably better, right? Because then I get a 16 here, so that's just already 32 pi, and then I just have smaller things to deal with. I don't know if that was a good idea or not, but I think maybe it was. 4 squared 16 over 4 is 4, minus 12 plus 10, so it's 14 minus 12 is 2, so that's 32 pi times 2. So I really hope that the answer is 64 pi. That seems like a really big number. Yeah, it's just right. Okay, good. 4 more problems to go. Okay. 27C. Okay, 27C. Man, I think this is just kind of like more of the same. Use the disk or the shell method to find the volume of the solid generated by a route in the region. Okay, so what did I say? 27C, huh? So I give you guys like the hard one. So we have y equals x cubed, y equals 0, x equals 2, and the line that we're rotating about is x equals 4. Okay, well, I have to decide whether to do this with shells or disks and washers, which suggests that one way might not be possible or one way might be harder than the other, so I don't know. Let's figure out what our region is first. I'm rotating about the x equals 4. Okay, so, yeah. So y equals x cubed between y equals 0 and x equals 2. So when x is 2, we're going to be way up here at 8. So something, something like that. That's y equals x cubed, but then in between x equals 2 and y equals 0. Okay, so therefore the region under discussion is this one. This is my region. The region enclosed by y equals 0, x equals 2, and y equals x cubed. So now I will draw y equal x cubed. And now what am I rotating about? I'm rotating about the line x equals 4. So here's x equals 4. And that's what I'm rotating about. So what kind of shape is going to be formed? Well, it's going to be like some kind of this type shape. Cha-cha-cha, cha-cha-cha, cha-cha-cha kind of thing. It's going to be some sort of volcano sort of thing. Okay, well, let's do it. I'm just going to use shells because why not? So because everything will just be a polynomial, it seems better. So I draw my representative rectangle, which is right here. I pick an arbitrary x value on the x-axis, which is just x. And then what happens when that shell gets rotated around the line x equals 4 is we get when that rectangle gets rotated around the line x equals 4, a shell is formed. And now I just need to find the dimensions of that shell. Well, the height of the shell is easy. The height of the shell in terms of x will just be x cubed. And the radius of the shell is the distance of the representative rectangle from the axis of rotation. So here the distance for a given x, the distance to the line x equals 4 is just 4 minus x. Alright, so I think I got this under control. This is not so different from the previous problem, actually. It's actually very similar. So let's do it. What are we doing again? 2 pi, the radius, which is 4 minus x, times the height, which is x cubed, times the thickness, which is dx. I think that's all. This problem is just the same thing. And I'm going to integrate from 0 to 2. It's actually easier than the previous problem we just did. There it is. Okay, so I get 2 pi, integral from 0 to 2, of 4x cubed minus x to the 4th dx. And I can just do this integral, so many integrals, x to the 4th over 4, so that becomes just x to the 4th, minus x to the 5th over 5, I guess. Evaluated at 2 and 0. What did I just say a second ago? It was a good idea to rewrite this as x to the 4th, 1 minus x over 5. I think I said to do that. Because then the numbers will be smaller. Just double checking all this math. Yes, all right. Okay, so I get 2 pi. Here is going to be 16, and here is going to be 1 minus 2/5, so that's 3/5. And so indeed, I get 96 pi over 5, I believe. 48, 97. Could that be right? I bet it is. 27C, 96 pi over 5. Man, I'm so good at calculus. Okay, 3 problems to go. Ugh. Okay, 44. Was this the kind of thinking problem? Oh man. 44, in all seriousness, I bet giant groan possibly came out of you when you saw this. 44 says, hey, remember that problem from the previous section which was so hard? Finding the volume of a torus? Let's do it again, but let's do it with shells. Yeah, let's go. Find the volume of a torus. And here's what we're going to do. We're going to take now we're going to start with the circle, x squared plus y squared equals little r squared. And we're going to rotate it about the line x equals big R. So, okay, I'm about to make a picture in a second, but hopefully you'll see that this is going to do the job. Let me think carefully about how I want to do this. Yeah. So, So here's the circle, x squared plus y squared equals little r squared. And this is therefore the point little r comma 0. But now, I think I drew my picture too big. Now I'm going to have this line x equals r. And when I rotate this about x equals r, then what I'm going to get is a torus. I think that's kind of clear, right? That this whole circle just gets rotated and we get a torus. Okay, well, similar to before, I don't think I need to do the bottom half because this thing is totally symmetrical. So instead I'm going to find the volume of like a half torus and then multiply by 2. And so here's where I'm at right now. I have this region and I'm going to calculate the volume of a torus by rotating this this green region about the line x equals r. Now the last time, because we didn't have the method of shells yet, we had to do some sort of convoluted thing by going sideways, and we had all these like plus or minus square roots. It was real drag. We're still going to have square roots, but now perhaps it's more elegant to just do this whole thing with shells. So here are my shell. Here is my shell, and for a given x, I can draw that representative rectangle, and when that representative rectangle gets rotated about the line x equals big R, I get a shell. And if I can find the volume of that shell, I can add them all up. Well, what is the radius of this shell? Well, the radius of the shell is the distance the shell is from the axis of rotation, so it's going to be big R minus x. And the height of the shell is just going to be the height of that representative rectangle. So that's just root r squared minus x squared. Okay, so if I'm doing this correctly, and I think I am, I'm going to do it here so I can go horizontally. What I have is 2 pi, the radius of the shell, which is r minus x, times, make sure I do this correctly, 2 pi, the radius of the shell, times the height of the shell, which is root r squared minus x squared, 2 pi r h dx. Yeah, that's just it. And now I have to go all the way from negative little r to negative r to r. So that's my integral. Is this integral any easier? Yeah, it is. Watch this. Something kind of cool happens. If you're extremely smooth, there are 2 options here. There's what I did for the first 10 years, which is do a u sub here in order to do this integral. But something even cooler happens. So okay, let's distribute